Can you hear me? Let's roll. So here we have the wind machine, a cutaway schematic of a wind turbine. And in general, we're going to always talking in general terms. We're going to have a rotor, which is made up of 2 or 3 blades. It's going to be bolted in general to a magnet can, which is essentially just a great big brake drum, if you think about it, lined with magnets on the inside of it, and which is going to be rotating over top of stationary copper coils. And when you pass a copper coil through a magnetic field, you get a pulse of electricity. When you have lots of coils, lots of magnets, you're going to have lots of pulses. All right. We're going to come off of these windings in 3 phases. We're going to have L1, L2, and L3. All right. 3-phase machine. We're going to come off a 3-phase wild AC, so it's going to vary in voltage and frequency as the wind comes up and comes down. It's going to be cyclic. And what kind of is this the kind of energy we can use right at the outlet? No, we have to condition it. So we're going to come off the tower with 3-phase wild AC, come down the tower and into an inverter, which is going to invert that from 3-phase wild AC into usable utility grade 240 volt AC. All right. So we're going to have a component involved in that. So those components, anything other than the wind turbine, we're going to call the balance of systems. So that may be charge controllers, it might be disconnects, it might be inverters, might be some rectifiers involved with that. But we're going to call those the balance of systems. Now, when we come off the machine, and with our 3 legs, L1, L2, L3, we have this yawing machine. When a machine turns in the wind, that's called yawing. So we have to we have this rotating bit, but we have the machine that's going to rotate around the tower 360 degrees. So we're going to transport that power to the stationary tower. We're going to do that through the means of a slip coupling. This is slip rings, 3 brass rings, L1, L2, L3. This is going to be stationary on the tower. And then we're going to have carbon brushes that are going to rub up against those slip rings, L1, L2, and L3. And that's going to be the yawing mechanism on the machine. It's going to be rotating around this stationary slip ring. And we're going to transport the energy from the machine through the brushes, carbon brushes, to the slip rings and down the tower on the leads. All right? So as part of our maintenance, every 6 months, when we go up and check out our machine, we're going to check out the health of these slip rings, because this is what's a vulnerable part, a part that's going to get dirty and worn, and we're going to clean it up, get all the schmutz and everything off the rings, get it nice and bright, and we're going to do a volt-ohm test, see what's kind of a resistance we have in the system, and we're going to check the health of the carbon brushes. How often do they have to be changed out? Not very often, maybe once a decade or greater. And if we have a lightning strike, this is going to be the most vulnerable part of the whole system. Lightning strikes. Let's talk about that real quick. So we have this great big giant lightning rod sticking up in the air, 100 feet, 120 feet, 140 feet, 160 feet. Maybe we have a guide lattice tower here. Main mast and then guide off in 3 different directions as an example. Well, what we're going to do is we're going to take and ground every piece of metal that goes down to the ground. So we're going to ground out all these cables and then go to earth. Going to take the main mast, ground that to earth with just a ground rod, put it down deep, and go over here, ground each cable, individual cable, the anchors, go down to the ground. So as the air moves across our metal bits and pieces, it's going to start building up a static charge within those metal pieces. So this grounding method is going to bleed off that static charge, make that tower less attractive to the lightning. We have three wind machines at our site, 3, 4, 5 PV systems, and 1 two solar water heating arrays, all metal bits and pieces being exposed to the air, building up static charges. They're all grounded to ground, ground to earth, and we're bleeding off that static charge, making it less attractive to lightning. We've never, knock on wood, we've never had a lightning strike on our components, on our towers, on our machines, what have you. But we have had lightning strikes come in on the telephone line and wipe out servers and computers and everything. So we're still vulnerable. Can we still get a lightning strike on a wind machine or a tower or an array? Absolutely. But this makes it less likely. So carbon brushes. The slip rings, carbon brushes, rotating bit, wear points, bloody blah. But this is the service part. We're going to, as a part of our service, we're going to clean this up, check the health of it. And then something that happened on this installation was on the inside of the tower. We couldn't see this because it's going down through the inside of the tower. The conductors were going down through a pipe all the way 126 feet down, but there was a little nub on the inside of the tower, and after 4 years' time, it has worn through the casing of the insulation on the wires, one of the conductors, and shorted out the system. So more on that later, but so we had other problems involved with this system too. Never even knew it happened. But every 6 months, we're going to check the health of that system, do service work on it, do inspections and grease jobs, and clean things up. So we get more bang for our buck. This is the body of a 10 kilowatt Berge. Here's where the blades would bolt into, 3 blades. Huge magnet can. Diameter is maybe perhaps about this big around. I think the weight of this with the rotor and the tail on is about 1,000 pounds or more. Huge machine, real heavy. And then the fiberglass nacelle, which has just some junction boxes underneath that. And then the tail bolts on to the back bit. So there's 6 wear points on this machine. The least complicated the machine, the longer the life is going to be. 2 bearings on the generator, 2 bearings on the yaw mechanism, and then 2 bushings on the tail. 6 wear points, right? Sealed bearings here, and then 2 brass bushings. Very simple. There's a million of these machines out there. This is a body of a 1 kilowatt Berge. Here we have the magnet can. This is where the blades bolt into. Magnet can, coils underneath that, stationary. The 3 phases coming out of the alternator over to the slip rings right here. Now we're looking down onto a 1,500 kilowatt, 1,500 watt Berge machine, looking down on it. Here's the rotor right here. This is where the blades would bolt in. Rotating rotor bits, magnets, and then the stationary coils. 1,000 watt Berge, smaller magnets, coils, the leads coming off. Now we're looking into the back side of a old 900 watt version of that machine right there, this Whisper. This machine is originally manufactured in Duluth, Minnesota, designed by Elliott Bailey, and he took a different twist on this. This machine's been out there for a long time. It's made for battery charging applications in cabins. You get above the 45th parallel above us. There's a lot of off-grid homes, a lot of off-grid cabin type situations, and that's what that machine was built for, charging up batteries. So it had to be affordable because the smaller the machine it is, the more expensive it is per watt to install it. So Elliott took and made a high-performance machine at a lower cost. How did he do that? Well, there's 3 things you can mess around with to improve or influence the output of a generator. You can mess around with the flux density of the magnets. So you can have cheap magnets, you can have expensive magnets, weak magnets, strong magnets. That's going to influence the output of the machine. The air gap, the gap between the magnets and the coils, is going to influence the output of the machine, and the RPMs. it's going to influence the output of the machine. So what Elliot did was he put in some pretty good magnets. You can see some hefty magnets there, bar magnets. And he decreased the air gap, which is going to increase performance too. Really close tolerances between the magnet and the coils. And he doubled the RPM of the machine. When you double the RPM of the machine, you can get the same amount of output with half the amount of materials. Half the copper, half the magnets, half the steel to get the same amount of output. So he increased the RPM of this machine and got away with less materials. So now you have something that's more affordable, more attractive to a off-grid or cabin owner, weekend cabin owner. So we're looking at the backside of this machine, older generation of this machine right here. So he has an extremely tight air gap, and at break time, you folks can come on down and take a look at the air gap between there. There's maybe about a 1/16 of an inch gap. All right, so as part of your service work, you're going to go up, climb the tower, and you're going to rock the rotor. What is the health of the bearings on this machine? So what assumptions can we make from a machine that has high RPMs? What kind of service life or bearing life are we going to have? Shorter bearing life, yeah. So every 6 months we're going to get up and rock that rotor. If we start getting wear on the bearings, what is that going to do to the health of our machine? We have a close air gap. It's going to start rubbing on the coils, taking the insulation off, shorting out the coils, and then we got a problem. So you're going to be every 6 months. You're going to be up checking the bearings. Bearing life. So this machine is made for low wind speeds, mediocre wind sites, not high wind sites. Bearing life, 10 years, 10 years. Bring it down, punch the bearings out, put new bearings in, and you're up and going again. You put this same machine into a high wind situation, like a 14-mile-an-hour wind speeds, which we see on the western side of Wisconsin, up in the Coulee region. A friend of mine had this same machine up on a tower, 900-watt machine, and he couldn't keep it on the tower. Bearings were failing. The machine was running at too high an RPM for too great a duration, and the bearing life just couldn't take it. Not only couldn't the bearings take it, but at that time it had two blades. It was a two-bladed machine at that time. Couldn't keep a rotor on it, and it had jumped off the tower a couple of times. So just couldn't handle it. This machine is made for low wind speeds, mediocre wind sites. Does a great job of what it's supposed to be doing. This is the axial generator. This is a generator design that Hugh Pickett uses for the proven wind machines, all the proven wind machines. And Ventura Wind, Elliott Bailey's new company, is using this axial generator as well, or pancake generator. So let's backtrack a second. So Elliott designed this machine and two others. Eventually sold it to Southwest Wind Power, and he reformed a company called Ventura Wind. Back up in Duluth, Minnesota now. He's up there. Just came out with a machine for prime time, made for prime time now. It was a beta machine out there a couple years ago. I just checked it out last night, and he's got something to sell now. So, the axial generator. So, this design influences the flux density. We mess around with the air gap, and then we're going to mess around with the RPM, but not speed it up, but slow down the RPM. This is an axial generator right here. So, we're going to have a disc that's going to have copper coils in it. That's going to be stationary. Then we're going to have, sandwiching it on either side, two rotor discs with magnets on. So we're going to have magnets. They're going to rotate with each other. So we're going to have north, south, north, south, north, south, north, south. And we're going to have tremendous amounts of flux density going across those coils on both sides of the coils at once. Going to decrease the air gap. Oh, nuts, I did that. We're going to have tremendous amounts of flux density, decrease the air gap. That's going to increase our production. But Hue slows down the RPM of the machine. So we're going to increase the flux density by a tremendous amount, decrease the air gap, slow down the rotor. What kind of lifespan is that machine going to have? Longer lifespan. Lower RPMs equal longer lifespan. In general, we can say machines that have a higher RPM are going to have lower upfront costs because there's less materials, more affordable. But in the long run, it's going to have a shorter lifespan and more service work on the backside. In general, we can say machines that have a higher or lower RPM are going to have higher upfront costs, longer life, and less in the service side and maintenance side. In general. Here's that machine. We're looking at the end of it. We have two magnet rotors flying over one stationary stator where we have the coils. Tremendous amounts of energy. So if we double the RPM of a machine, we can get away with half the machine to do the same amount of work, half the materials to do the same amount of work. In general, we can say that the high-speed machines tend to be the Southwest Wind Powers. And in general, we can say that the low-end machines tend to be the Provens, the AWPs, the Aries, the Bergies, and the sort. High upfront costs, though. Huge upfront costs, but longer lives. Do the Whispers work? Absolutely. They're great for what they're made for. Battery charging applications. Tail configurations, we're going to be talking about upwind and downwind machines. In general, a upwind machine is going to have a tail, and that tail is going to orient the rotor into the wind all day, every day. Very responsive to the changes in the wind. So we're going to have wind coming, upwind machines have, the wind is going to hit the rotor first and then pass the tower. That's an upwind machine. A downwind machine, generally, a downwind machine doesn't have a tail, but not all tailless machines are downwind. So in this case, this machine, this is a proven 2,500 watt machine. Here's the tower right here. Here's the rotor disc right here. So wind is going to come across, hit the tower first, then the rotor. The rotor is the tail that it's going to have turn itself around and have equal pressure on each side of the rotor all day, every day. A little less responsive to the changes of the wind, but less materials. Is any one better than the other? No, not really. It's just manufacturer's preferences. A characteristic of a downwind machine is as the wind passes the tower, behind the tower, we're going to have turbulent air in the wake of that, in the shadow of that tower. And as the blade comes through that shadow of the tower, we're going to have a popping sound. It's going to pop, 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 pop. And to what degree what kind of noise is coming off that, I can't. I can't say. The machine out in my backyard does that. It's a downwind machine. It's actually that machine right there, that Proven, this guy. And yeah, you can hear it. And it depends on where the rotor is oriented and where you are in relation to that rotor. If you're off to the side, it's a little bit more noisy than upwind. I don't know. Well, what's too noisy? I don't know. To a neighbor, it could be too noisy. So this is the original blade off that machine, made out of recycled milk jugs. And this is the redesigned airfoil for that machine. And when Proven came out with it, they said that this would eliminate that popping sound. Didn't believe it. Threw on new blades, virtually silent. All in the design of the airfoil. Southwest Wind Power has the Skystream machine. They did a hook-shaped scimitar hook-shaped blade on that machine. said that would take care of the popping sound. Speed control. All wind machines have to have some sort of speed control on it. And again, if we look back at that chart we saw earlier, our machine's going to run mostly see the 7 to 12 mile an hour wind speeds most of the time. But we're going to see 20, 30, 40 mile an hour, 50 mile an hour wind speeds any time of the year. And so we have to have some sort of form of protection for that machine so it doesn't overproduce. So we're going to limit the production of that machine. And that's called governing. And we're going to have all sorts of different methods to do that. Most of them are going to be passive activating, and that's the cheapest method. Or we're going to have active governing. So when we govern a machine, if we look at the power curve, the power output of that machine, this is wind speed, this is higher, this is power. So as wind speeds increase, we're going to have exponential ramping up of power. It's going to climb in power very fast, exponentially. We're going to come up to peak output at X amount of wind speed. We'll say 30 miles an hour. And as wind speeds increase past that point, we're going to see a regulation of the machine, and the power curve is going to change. It's going to plateau and maintain 100%, or maybe it'll ramp up, plateau, and as wind speeds increase, it'll fall off slightly and then plateau. There's a few machines where they'll ramp up real fast, and as wind speeds increase, their production just drops off dismally. So we're going to see all sorts of different power curves as it relates to the governing of the machine. One of the old school methods, and we'll see this in many different configurations, is to mount a pivot point on the machine that's offset from the center shaft of the generator. So as wind speeds increase, we're going to have equal loading on the rotor, but we're going to have a pivot point below the shaft of the generator. So it's going to want to tilt back on itself, or tilt to the side, walk around the tower. In the tilt back method, the machine is going to tilt back on itself, and the wind is going to see less swept area. And as wind speeds decrease, springs are going to pull it back down into position, and the wind is going to see the full swept area of the machine. And as wind speeds increase, it'll see less of the swept area, but maintain maximum output. Here's a Lakota. The wind baron used this method also. Here we have the rotor, center shaft, and then the pivot point. So as the rotor gets loaded down, it's going to tilt back on itself. And then the springs, stainless steel springs, 2 of them, will bring it back down into position. So when we do service work on this machine, we're going to check the health of these stainless steel springs. What does the hooks look like? What do the eyes look like? Also, here's the power cord right here, coming out of the generator into the tower, into the body of the machine, and then down the tower. What is the health of those conductors right there? Could have chafing as it tilts back on itself. Remember these conductors right here? We had chafing on the inside of the tower. Caused problems with that installation. Here's the machine tilted all the way back on itself. There was problems with this wind baron design, where when the rotor was unloaded with the wind, the springs would bring down the machine and slam it back into position. It wasn't very subtle. It wasn't not much finesse involved with that. But slammed back into position. The Lakota changed that design slightly and got away from that. Now, instead of tilting back, we're going to have a machine that's going to be, the center line of the machine is going to be offset from the center line of the tower. All right? And it's not this machine, but it's similar to this design. So as wind speeds increase, the rotor is going to be loaded down, and it's going to tend to want to walk around the tower. The head is going to want to try to move around the tower. And as it moves around the tower, there's going to be, here's the tail that's going to stay oriented to the wind all the time, all day, every day. And there's going to be a pin on the backside with a compound angle. As when as wind speeds increase, load down the rotor. The rotor's going to walk around the tower. The tail's going to stay oriented to the wind, and as the head moves away from around or moves around the tower, the tail is going to lift up and stay oriented to the wind. As wind speeds decrease, the tail falls down. The weight of the tail brings the tail down. Gravity brings the tail down and brings the head back in alignment with the wind. So we're going to have this kind of dealio going on. All right. Another side-facing configuration is what the Whisper uses. Instead of the tail moving, we're going to put the compound angled pin on the head, and as wind speeds increase, the rotor is going to tilt up and away from the wind, and then the weight of the head is going to bring it back down into position. All right, very simple designs. Here's a Chinese storm. Here's the tower and the center line of the machine. So the rotor is going to try to walk around the tower. Here's the side face, that machine there actually. Here's a machine that's furling, so it's governing right now. The wind is seeing less of the rotor right now, but still maintaining output. This is a different type of speed control. This is what's used on the Proven. This is the downwind machine right here. And the Proven is going to use a different kind of, it's going to fold the blades back. And this is the machine that Hugh Pigott designed. And he was sitting down, legend has it that he was sitting down at the pub farting around with a napkin, and he came up with this folding design, and it's based upon origami. And at break time, you can come on down and take a look at the blade configuration. So the blade's going to be held up into position by the 3 springs you see on the photo. And as wind speeds increase, it's going to fold, the blades are going to fold this way and then backwards into a cone shape. And it works very effectively. So it's a nice rubber hinge right here, backed up by some cabling. Here's the 3 stainless steel springs holding that rotor out straight. And it used to be 2 stainless steel springs, and they bumped it up to 3. And so as wind speeds increase, this rotor is held out straight, 11-foot rotor. And as wind speeds increase, the blades fold backwards into a cone shape. And there's footage of this machine running in a hurricane, and this 11-foot rotor is down into a 3-foot cone, maintaining 2,500 RPM, 2,500 watt output. And as wind speeds decrease, the stainless steel springs bring it back into place. Very simple system. So this is our machine. This is on a tilt-up tower, so we can't climb this tower. We're going to lower the tower, do the work right down here. That's what these folks are doing. And this machine is built in Scotland, came in a crate. We assembled it as the manufacturer said you should. And in Scotland, they use the metric system. Here we use the English system. And so we followed the specs, the manual, and how to assemble this. And there's a length that these springs need to be in order to have proper tension on, so that the blades don't fold too early. All right. Well, there was a problem in the conversion from metric to English, and these springs were too slack. There wasn't enough tension on them. And a 2,500 watt machine was producing 1,800 watts. So, but we didn't know this until we got the machine up, got it running, and over a period of time, we looked at the outputs relative to the wind speeds. We're like, well, this isn't doing it. It's wrong. So we started asking around and talked to other folks that had this wind machine. And yeah, they're like, yeah, these springs aren't tight enough. So we brought the machine down, tightened them up an 1 7/8 inches, and now we have a 2,500 watt machine that puts out 2,500 watts. But we wouldn't have known that had we not looked at the outputs, talked to other people. We wouldn't have known that. We would have a 2,500 watt machine that puts out 1,800 watts. You know, and then you wonder why wind doesn't work. So there was a problem in the conversion. Since then, they fixed their manual. This is a spoiler system used back in the day. So we have these spoilers that are going to rotate into with the rotor, and as wind speeds increase, they're going to kick out and slow down the rotor. Still used today. Vestas, which is the 30, 60, and 90 kilowatt machines, smaller Vestas machines, and the Enertex use this. But they have a spoiler that's going to be on the tip of the blade, and it's going to follow the blade through its rotation, and as wind speeds increase, it's going to kick out and slow down the rotor down. Works very effectively. When we do service work, we're going to look at the bushings on that spoiler and look at the spring that brings it back into place. Or what generally happens is, over a period of time as the spoiler works itself back and forth and eventually falls off and then throws your rotor out of balance. Still used today, though. Very effective. Elliott Bailey has a system where, you remember I was telling you he has this new machine out, the Ventera? He has a blade that looks like this, but only larger, longer. Same design. And he took and cut the blade, like the last third off, put the last third on a shaft, on a helical shaft in a spring. And so normal operation, the blade looks like so. As wind speeds increase, the outer third of the blade pulls out from the center of the main blade and puts a twist in it, just destroying the airfoil, slowing it down a bit, maintaining control. What kind of maintenance and service is going to be on that? Who knows? I don't know. It's yet to be seen. This machine hasn't been out there very long. Just out for prime time. Must have been this year. All sorts of clever designs. Now we're going into the active governing of the rotor. The Jacobs boys out in Minnesota, they took and had on their machines, they had a wooden blades bolted to this mechanism here. As wind speeds increase, flyweights would come out from the center of this governor, activate a gear mechanism, and then pitch the blades, making them less aerodynamic but maintaining full RPMs. Lot of metal involved in this, more sophistication, more involvement with this governor. So they retweaked the design, came up with this. So now we have the wooden blades slid onto smooth shafts, three blades slid onto a smooth shaft, held into the center with springs, right here. And as wind speeds increase, the blades will pull from the center, and as they pull from the center, they'll pitch. And this actuator, this spider on the backside, will synchronize the pitching of those blades. And as wind speeds decrease, the springs pull the blades back into the center. Still used today. Here's this is a 3120 Jake, and we're looking on the back side of this governor. Instead of one spring, there's two giant springs. On the front side, here's the actuator right here, the spider, which synchronizes the pitching of the blades. And then the blades are on a smooth shaft. Here's a shoe right here, shoe, onto a smooth shaft. So when we do service work on this machine, now we're going to take a grease gun up with us, and we're going to and a roll of black tape. Going to climb up the tower, pull the rubber boots off the knuckles. We're going to force grease into there, and we're going to put the boot back on. And over a couple of years, the UV is going to destroy the rubber boots. So we're going to wrap it up in black tape. Then we're going to have some grease zerks on the blades for the shafts, and then we're going to have grease zerks on the synchronizer or the governor, and we're going to inspect the health of the springs as well. So on I know on a 3600 watt Jake has a 7-foot wooden blade, Sitka spruce blade. That 7-pound blade at full RPM, full production rated output of that machine. There's 700 and some pounds of that blade weighs 700 and some pounds. The G-forces involved. Now think about this blade. This is a 15-foot blade, and I think it weighs about 70 pounds. Think about how much weight is pulling out from the center on that machine. You know, you take a 26-inch, 27-inch bicycle wheel, and you hold the axles and you give it a spin, and the gyroscopic forces involved with that. Think about a 31-foot rotor. What kind of forces are involved with that? Huge. as you try, and you got a wind that's trying to wrestle this rotor. Huge forces on this. So we're going to do our inspections on this every 6 months. So now we're going to take. Okay, this is good. This is a good spot to ask questions. Let's go to the remote sections first. And I don't know who you all are, but if you have a question, let's pipe up just now. Anyone? 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 Bueller?
Tipton has a question regarding the resources.
Yeah.
This is kind of off the subject, but just regarding the resources, we have the PowerPoints at our sites, but we noticed the books there. Are there any articles or anything that we're missing that we could get our hands on?
Oh. Yes. At break time, maybe we can. Yeah, in that version, there's some articles in the back of each section, and those articles I got directly off of Home Power Magazine. I typed in wind, and I printed off some select articles. One which you absolutely should have is called the. Jot this down real quick. It's called the Wind Turbine Buyer's Guide. You're going to want that. How to buy a wind electric system. All these are from Home Power Magazine.
Mary, this is Chad. Maybe what we can do is collect this information and get it out to you at the counties. And if there are some participants who leave their contact information, we can get it to them. Is that acceptable?
That'll be fine. Thank you.
You bet.
Okay. Yeah, sorry about that.
We've got a question here in LaPorte.
Yep.
Hi. Pardon me. What kind of resources are available for maintenance education for these units?
Oh, boy. We're actually, we train service people at our site as well. And I think Solar Energy International is just starting up a maintenance and service program also, and that's the only ones I know out there. If you look at the installation service manuals of any of the wind machines, you're going to find virtually nothing, and it's all based upon on-the-job experience. So what we're doing is we're taking and creating service reports. And trying to document what you do to a wind machine, a particular brand of wind machine, when you do the service work. But there's nothing out there. The service manual's virtually useless.
One quick comment, too, is Ivy Tech here in Indiana, the community college system is working on a program for operations and maintenance. It's in the startup phase, but you're right, Clay. There are.
Oh, you're talking.
I'm sorry, I'm over here. But you're right. There is a need for more resources put toward O&M.
Oh yeah.
Resource.
Yeah, boy. If there's any technical writers out there, this is a niche for you. There's nothing out there. Absolutely nothing. The only.
We have a question.
Yeah. Go ahead.
Go ahead.
Yes. You were talking earlier about when they test these machines, they test them on the European standard. In Europe, they use a 50-cycle electric system, and here in the United States, we use 60-cycle.
Yeah.
And what I was wondering is, are these tested on the 50-cycle or 60-cycle systems?
No. It's they're just taking the basic parameters, like based upon wind speeds. How does it relate from wind speeds to output? This, that, and the other thing. It's not based on the electronic side. Just go to the Small Wind Certification Council website, and they'll give you that information. But it has nothing to do on the electronic side.
What he was saying there, what he didn't really say, but what happened.
We have a question from Lake County.
Yeah.
You referenced grounding. What determines the size of the ground rod and the conductor for grounding? Is that the National Electrical Code?
Yeah,
and another question is monopoles. With a monopole, do you need soil boring to determine the ground that you're putting your foundation in? And I've got one more question. When you're doing the maintenance on a rotor, how do you stop the rotor?
Oh, well, let's start with the easy one. All machines are going to have some sort of braking mechanism. This particular machine, I don't know if you guys can see it. The Whispers, the Provens, most machines have some sort of electric braking system. They're putting out three-phase wild AC, and what you're going to do is you're going to short out all three phases together. Puts the ultimate load on the rotor. So as you try to turn it more resistance is involved. And I actually have the three phases wire netted on this one. As you try to spin it, there's resistance. On this axial generator, the three phases, 1, 2, and 3, aren't shorted out and it turns freely. The Jacobs, the Big Jakes, the Endurance, and a couple others have a mechanical brake on it. Usually a rotor with the calipers, either mechanically or air actuated or hydraulically actuated. So that's how we're going to shut down the rotor. We're going to stop the rotor before we go up on the tower and do the service work. And the electrical braking is the most popular one. It's the easiest one to do. Grounding. The grounding is going to be spec'd out through the NEC. And the diameter of the ground rod, what is that, 5/8? Just standard issue, nothing special, 8 foot long. And depending on your soil type and the soil dryness or wetness is going to determine how many you put those, how much grounding you do, and the depths, how many ground rods you have. The drier the soil, the less conductivity, the more copper you have to have underground to do the same amount of work as wet soil. You know, like if you're in Colorado or something, they put lots of huge grid works of grounding halos or mats, subgrade, to do the same amount of work. Get that static charge dissipated into the ground. Monopoles, different animal. We're going to talk about tilt-up towers, freestanding towers, and guide lattice towers. Monopoles are extremely expensive. Have lots of concrete, lots of steel involved to hold that pole up. It's just like a giant light pole in the ground, and lots of stuff going on there. And I can't remember exactly what the question was, but do you have experience with monopoles? Can you talk briefly about that?
The monopoles is what they do on a lot of them with the sky streams. They'll actually put the rod down, and certain counties will let you put the grounding inside the concrete. Some counties will let you do that, some won't. They have a plate, I forgot what the plate name is, will actually put down in the bottom and run a 6 or a 10-foot grounding wire up through the bottom there. It just depends on the county, on where you're at. Some counties are easier to deal with than others.
And as part of the NEC, they're requiring grounding out to the rebar cage and that, and that's I think just I don't think that's very smart. Any other questions?
We have another question from Hendricks.
Yeah.
Have you researched the new style of bearings that are non-metal, that are self-lubricating, and they're the ones I've experienced with run up to about 1,000 RPM? That's first question. The second question deals with a possibility, and probably in defiance of physics, but putting a prop on the other end of your wind turbine, but changing the pitch design, and maybe gaining enough at low RPM enough, or I don't know the square, but would, I think, gain the wattage and power output at a lower RPM on a specific wind turbine.
There have been manufacturers that have put on counter-rotating rotors, multiple rotors, onto the wind machine, and they work fine, they produce energy, but they have to compete with other wind machines too. And if they're too expensive, people aren't going to buy it. Self-lubricating bearings, there's, I don't know who's using them, but again, they're expensive. They have to be able to compete with other wind machines. There's only, 5 manufacturers in the United States currently? So we have these 5 people who are all mom and pop, except for Southwest Wind Power, all mom and pop shops. They They do something else to put food on the table and specialize, and then they have wind on the side. For example, like Wind Turbine Industries, Prior Lake, Minnesota, I had to take an inverter up to them. If they didn't have a wind machine out back, I would have never known it. It's a machine shop that makes wind machines, a machine shop that makes wind machines on the side. Small batches. They do a run of 20, run of 50, then they take orders, then do another run. It's just mom and pop operations, essentially. So they have to be able to compete with all these other machines that are out there. And now we got the Canadian machines coming in as well, and a couple of Europeans. So I don't know. Are we going to see more of those self-lubricating bearings? Maybe. Depends on cost. Yes?
On your permanent magnet generator alternator over there, do you hook that up in star or delta, or do you switch back and forth?
It is configured in a Y configuration. Yes, it's in a Y configuration.
Okay.
Mm-hmm.
Question from Bartholomew County.
Yeah.
Go ahead.
Long-time listener, first-time caller.
The question I would have, how much effort do you have to put in to condition the power to connect it back to the power grid?
How much effort is going to be involved? Well, we're going to connect it into an inverter, take our 3 leads, or L1, 2, and 3, connect them into the terminals on our inverter, which may be a Windy Boy, maybe the inverter manufactures the wind industries, Wind Turbine Industries inverter for the Jake, or the Berge has a Xantrax inverter made for it, or we can use the Magnatech, Power One Magnatech has a wind inverter also. We're just going to put our leads into it. It's going to do its magic, and we're going to get utility grade 240 volt on the output. So what we have to do, we just are going to hook up the terminals, and that's it. And then it's going to do its magic. But we only have like 4 inverters available to us. There's the Windy Boy by SMA, the Magnatech by Power One, and then the Xantrax makes an inverter for the Berge, and then the Wind Turbine Industries has their own inverter for their machine. That's the only thing that's out there. Unless we run it through a battery pack, then we have other options. That probably didn't answer your question, did it?
That was a good answer. Is there something else required by the utility to make sure they're synchronized, the power that you're generating is synchronized to theirs?
Yeah. Now, this inverter is going to only operate in certain parameters, and it's going to match the utility pound for pound in voltage and in frequency. And if it falls within fractions of percents out of those parameters, the inverter automatically drops out and physically disconnects from the utility. It's called anti-islanding, and they don't. If the utility goes down, the inverter goes down, and that's called anti-islanding. So that you're not producing electricity, putting it out onto the utility, and the inverter is going to match the quality of the utility in frequency and voltage and waveform, so that you're not putting out something different. So that's a part of the electronics. All inverters that are utility intertied are going to operate with the utility and match it pound for pound. Capiche? Anything else? Yeah.
When you were talking about the different speed controls, it just seems like 3 blades, making sure that they magically all work in tight parameters together with springs and such, or balls. Just seems like magic. So if one is a little bit off, what happens to the power or even the safety of the machine?
Well, they're going to be in the activated governors, the one that's like on the Jake, where they have synchronized pitching of the blades. That's going to be set in the shop, and that'll be set in the shop. If it varies from that, yeah, there could be some performance issues of that. But that's going to be set in the shop, and then once it's set, then it's there. What it's going to do, if it goes out of sync, I don't know.
What about the Jacobs there? If one furls back and the other 2 don't, you've got a lot of centrifugal force.
Oh, on the Proven?
Yeah.
Boy, you'd have a rotor that's flopping around out there. Yeah, you'd have some issues up there. Yeah, absolutely. So he's asking about the proven where you have the 3 blades that are held into position by 3 springs. What if a spring set broke off? Yeah, you would have some issues there. Yeah, absolutely. But again, you're going to be on top of the service. You know, every 6 months you're going to be checking this out. If you don't check it out, someday maybe you're going to have a blade flopping around.
I think she means under normal wind conditions, if you get a gust on one side, say you got a 25 foot,
Mm-hmm.
and it furls one blade back.
No, not going to happen. No, because it's going to have even loading on the rotor. Going to be even loading on the rotor. Mm-hmm. Yes.
How reactive are these speed controls to gusty winds?
Oh,
I would have done the same thing.
You don't have to hold it down.
How responsive are the governors to the wind speed? Here's an example. Remember that 2,500 watt proven I have in the backyard? Okay, that's hooked up to analog meters. So we're seeing pretty much real time on the analog meters. I've seen a 2,500 watt machine peak at 3,600 watts. And it was in a January in strong winds, about 30 mile an hour winds. So we're looking at outputs, and then it would gust up to 40, 45, and so the needle would just bang up to 3,600 watts. Governor would kick in, and it would bring it down to 2,500 watts. Winds would come down, it would fall down below. Winds would bump up again, and we could see by the metering the action of the governor. So power would come up, governor would kick in, bring that power back down again. So we're seeing these spikes, and they would come back down, even out, spike, even out, come down. On the Jacobs at the office, in gusty winds, we're going to hear a slapping sound of the blades as they come back into pitch, as they pitch and unpitch. We're going to hear a slapping sound. So quite responsive. Yep. Yes, quite responsive. Yep.
There's a lot of flexing going on up there.
Oh, sure, absolutely. Yep, absolutely. Mm-hmm.
I want to touch on that
Another
just a little
question
bit.
from LaPorte County.
Oh, one sec.
Go ahead. I wanted to touch on that a little bit just to let you know about the dynamic braking. And the Sky Streams and the Mariah Power, they have their .com. The electronics is what happens with those is with the dynamic braking. They're actually monitored wirelessly on your computer or your laptop. And as what happens in a lot of those is there's temperature sensors, there's RPM sensors, there's a bunch of sensors in this thing that controls that. So if it's going too fast, is what happens is it'll slightly put a little bit of the dynamic braking in where it'll slightly put the legs in.
Yep.
So it'll actually make the unit run more efficient, and that way you don't have to worry about burning bearings out, burning the windings out, so you're not going to get those peaks up real high and down with a lot of the newer technology coming out today with the electronics.
Yep. There's a couple of manufacturers using electronic braking to control the maximum output of that machine.
Right.
Yep.
And it's a lot easier that way, so if something breaks down, it's a computer part that broke down. Go up, pull a pin, pull some plugs, put a new part in, and go. But you can monitor it right there yourself.
Yep. There was a question, was it LaPorte or something like that?
Yes.
Yes. What type of liability, property liability changes have you seen for owner-operators?
As it relates to the utilities?
To property owners.
As it relates to property owners.
Well, where I live, I'll use where I live as an example. County zoning wants to know where you site that wind machine so that if it should fall down, it falls within your property lines. If you're connected to, so that's what I know. If you're connected to the utility is going to have a big contract that you're going to sign, and in that agreement, you're going to have a certain amount of liability insurance involved with that. In Wisconsin, it's a general $1 million policy. Do you know what your utility is?
No, I'm sorry.
It's just general standard issue homeowner liability.
Gives attention. I can answer that question. It's $50. That's what I sell for a living.
Oh, yeah.
I've got 8 windmills insured. It's $50.
Oh, tell us what's the
It's like a wood burning stove. If it's approved and it's properly installed, they're still playing with what to charge, but that's what it's been for a couple of years.
Cool. Very good.
Extra 50 per year.
Oh, there you go.
It's really minimal.
Just tacked on to the...
And I look for that to disappear.
Okay. And that's just tacked on to the homeowner's policy.
Farm owner, typically.
Yeah. Cool. Very good. Thank you.
You mentioned that some of the manufacturers in their designs changed the RPMs.
Mm-hmm.
What design factor determines the RPMs?
It's going to be a function of all the pieces working together, but in general, and we're just talking in generalities, in general, the thicker and wider the blade, the slower the machine is going to run, and the thinner and narrower the blade, the faster it's going to run. But also we have to take in consideration air gap, of the between the magnets and the coils, and blade length factors into that, and flux density factors into that. But in general, as it relates to the rotor, thinner, narrower blades are going to run faster, thicker, wider blades are going to run slower, in general. Okay.
Another question from the board, please.
Okay.
Yeah, if the utility company goes down through a windstorm or the lines break or something, what happens to what's happening with your machine?
Okay, we're going to talk about that in just a little bit, but the inverter is going to physically disconnect from the utility so that you're not putting power out onto the dead lines. Number one, that's called anti-islanding. All inverters do that. Number two, what's it going to do with your machine? So now you're unloading that machine, and it's going to freewheel. So the rotor's going to take off, and it's going to freewheel. Most machines are built to do that. There's a couple of machines that you'd have to physically go out and shut them down. Does that make sense? Okay. Size categories. So we're going to take these machines. So our upper end of of our small wind category is the 100 kilowatts, all the way down to say like 400 or 500 watts production. And we're going to break this up into three categories. First, we're going to talk about on the lowest end is going to be the battery charging. We're going to do just battery charging with these machines, and they're going to be light duty, made for low, mediocre wind speeds, inexpensive, upfront costs generally, and they're going to come in low voltage configurations, 24 volts or 48 volts. And on the upper end of this scale, the division line, we may have a high voltage configuration available also. High voltage configuration meaning it's going to run maybe at 350 volts wild AC. And then the middle class, the middle section, we're going to start out with those crossover machines, which are going to operate at high voltage. And they're going to supply a portion of our needs for our home. We're talking like a 2,500 watt proven, a 2,500 watt ARE would be involved in there. And that's going to take us all the way up to the 10 kilowatt ARE, 10 kilowatt Berge is going to be on the upper end of that scale. That's going to provide all of our homes, all of our electrical needs on an annual basis. The next category is would be the machines that are going to supply a farm, a portion of a farm or a commercial operation, a portion of their energy needs. And that would be from, a 20 kilowatt Jake all the way up to 100 kilowatt Northwind 100. So we have these huge broad ranges, and we're going to just talk in generalities. From the cabin generators to the middle class section, the home size machines, all those are going to be direct drive, with one exception. They're going to be direct drive. One turn of the rotor equals one turn of the alternator. All right, and that machine is going to turn all day, every day, whether there's production or not. If there's a breeze, that rotor is going to be turning. On the upper end, beyond that, from the 20K Jake to the 90 kilowatt PGEs, those are going to be gear driven. So one turn of the rotor equals many turns of the alternator. So now we got a gearbox involved in there. More moving parts, more sophistication. So we're going to start on the lower end. We're going to start with what's available. Southwest Wind Power manufactured this came out of the marine industry, made for charging up batteries on sailboats. Worked great. Works great for that. Then Y2K rolled around, and there was an opportunity to make some money. And so the manufacturer started selling this machine. You put it up on a fence post, put it up on a piece of pipe, what have you, bolt it to a building, charge up a battery pack, and when the grid goes down at midnight Y2K, then you have power. And if you need one, why not have 6? They've produced, well, it's 400 watts and used to be rated at 40 miles per hour. Now they bumped that down a little bit. 2,000 RPM, extremely high-speed machine. They end up producing almost as much energy in the box as they do out of the box. The old, and you can buy these on the internet. Still can buy them. Work great for marine applications. Battery charging for marine applications, totally fine. The old speed regulation for that machine was this is blade off of that machine, would be to flex the blade when it started reaching governing speeds, 40 miles an hour, and called blade flutter, and it sounded like a chainsaw in your backyard. I've seen 3 of these machines. Only one of them has its blades on yet. Kurt Nelson up in Cornucopia has his on Lake Superior. So he has his shop on Lake Superior, has a small wind machine, this charging up batteries. Works great. If he forgets to shut down the machine before he goes home, and a wind comes up off the lake, the rotor takes off, you have that blade flutter, sounds like a chainsaw, and the people that live next door to the marina, they call Kurt up, say, Kurt, shut your wind machine down. So he jumps in the car, drives 15 miles, shuts the machine down. And it's always at night. So that's one way they regulated the output of that machine. The other way now is to dynamically break it, slow it down dynamically, short out those windings. So you can take a look at these. Southwest Wind Power, this is Elliott Bailey's, that's that machine right there. Elliott Bailey built this in Duluth, sold it to Southwest Wind Power. Very nice machines, made for battery charging applications. That's what they're made for. Low, mediocre wind speeds, work great. 47 pounds, now we're dropping down in RPMs. As we go through, look at the weight and look at the RPMs and look at the cost. Great machines, do an excellent job. Now that's a 900 watt machine. Now we go. Here's a 1,000 watt machine. So we went from 47 pounds up to 75 pounds. Went from 1,000 some RPM to 490 RPM. We're slowing down the rotor. This manufacturer's got a heavier machine, slower RPM, almost about the same amount of cost. So this machine's going to last probably longer in heavier winds. Nice machine, works great. Berge makes a good product. Skystream 3.7. This is in kind of one of those crossover machines. This is a very unique machine. Nothing like it out there just now. So remember when I was talking about those downwind machines, as the wind is going to hit the tower first, then the blades. We have the shadow, tower shadow. So as the blade passes through that shadow, we're going to get a popping sound. Well, this is that machine where I said had the scimitar-shaped blade that would eliminate that popping sound. I don't know if it has or not. What's your opinion? The scimitar-shaped blade of the Southwest Wind Power, I've not heard. I've heard one Skystream running, but I was focused on some other stuff. So
no, they still make noise. You'll get a lot of the grinding and you'll get. It's a winding noise, what you're going to get out of it. And then, but you got to look at it this way: the higher up they go, the less noise you're going to hear, and the higher wind speed, the wind will actually be louder than the unit itself.
Yeah, I've only seen one of these machines running, and it was in downtown D.C. and I was focused on something else. I was waiting for this other wind machine to fall over, actually.
Let me touch on something on that one. The only thing that we see with these machines is that if the pole isn't perfectly level, then the unit wheel, it'll always fail safe for one area. Well, then where they need about a 9 to 10 mile an hour to actually make them spin and start turning, then they're always on that downhill side. So you need 2 or 3 more miles an hour to actually push them up that hill. And then they're coming out now with it's still a monopole, but it's a 2-piece pole. So now you have to slide another pole into the other. Just because you actually have the pole on the bottom straight doesn't mean it's level at the top.
Sure.
So what we're doing is we're actually taking a string, putting it on the very tips of the rotors, and then you let the dynamic braking go and let it turn just a little bit to the string will touch the other tip. Then you can adjust it and you know it's perfectly level.
Yep.
Then once it goes, then the string flies off.
Sure. This is a downwind machine.
The cost that I see up there, is that per unit cost or is that installed cost?
That is just for the machine head. It's not
per
tower,
unit cost.
that's not labor, that's nothing. That's just for the machine.
Thank you.
Yep. So this is a downwind machine. Something that's unique to this machine is that they're generating 3-phase wild AC instead of coming off the tower, down the machine, off the machine, down the tower to the balancer systems with 3-phase wild AC. They're inverting it right at the machine head. So we're generating 3-phase wild AC, running it through an inverter, and then down the tower is utility grade 240 volt. So essentially, it's a plug-and-play system. That's what they're telling you. So you put up this machine, come down with 240 volt, plug it into a breaker. A couple other things involved, but essentially plug it into a breaker, and you're done. You're not messing around with balancer systems and that in your garage, in a basement, what have you. Some things that some cruxes, which may or may not be a problem, long as it holds out. If the inverter goes down, you got to go up on top of the pole and or tilt it down and work on it. How often do inverters go down? I don't know. Not very often. I have seen and heard of cases where the O-ring, this whole top lid of the machine right here, this whole top lid lifts off, and underneath that is the inverter. There was a guy I was just talking to a couple weeks ago. The O-ring blew out, and it got water down into the case, and it ruined the electronics because this is all circuitry down here. Shorted out the circuitry, and I think it froze in there as well. I can't remember. Yeah.
It's what they did to have an update on that because of the vibration of it. The bolts actually in the top of that unit vibrate loose. So what they did was they came out with a new O-ring kit. Then you have to put silicone around the top of it. Then they've got blue Loctite they want you to put in there to actually lock it down. Yep. The second problem with this unit is when it's running, especially this year, we had a lot of these go down. I mean, a whole bunch of them. The problem was it got so cold here, the unit was running, and you got to remember, everything is inside there. It's so hot and warm inside there. Then you've got the freezing cold outside. What's it do inside? Condensation. A lot of condensation built up in these units. So we're going back, tilting all these units back down, putting the new kits in, and then down at the bottom of them, I should have brought the unit here. I go to Indianapolis after this. But down in the bottom, there's a well down there, right where the winding is and the magnets. Well, the condensation is dripping all over the inverters and everything with this one. It's coming down the sides, and it's puddling up down there. So then it gets into the winding, throws all that moisture around, or it's freezing. So the answer to it as of right now is to drill a hole in the bottom. But it still doesn't fix the problem with the condensation problem.
Sure.
Because we've had a lot of calls the units aren't running.
This machine's been out there like maybe 3 years as a beta unit, and on the street for about a year or two. There was lots of troubles in the beginning ironing out the issues.
Well, that's with any wind generator. They're all going through phases. And I think that falls back on the reason why there is no technical class out there, because every wind generating company out there is still updating their units.
Next up is the AWP 3.6. This machine was developed by Hugh Piggott. Engineered by Hugh Piggott and for Zimbabwe, if you remember that. Originally rated at 900 watts, brought into the United States, now rated at 1,000 watts. There was political unrest in Zimbabwe, so they moved the manufacturing to South Africa, bloody, bloody, blah. Couldn't get parts or anything. Now we can get parts back again, and they're bringing it into the United States. Low voltage machine. Let's talk about low voltage, high voltage machines. This is our first machine, which is one of those crossover units where we can get it in 24, 48, or high voltage configurations. This is the Robert Preuss's ARE 110. Robert Preuss imported the AWP into the United States. Then he couldn't get the parts anymore, couldn't bring the machine in. So he took that same machine, retweaked it. This is the one that was real sloppy. Tightened up the air gaps, tightened up the quality of the machinings, better magnets, and he took that same machine and now it produces rated at 2.5 kilowatts, over double the output. So he took that design, retweaked it, and it has a better product, a better mousetrap. So let's talk about low voltage versus high voltage machines. This is our first crossover. So in my backyard is a 2.5 kilowatt proven, and what we got going on is, so we have the wind machine and a 130-foot tower, and we're producing, it produces 2,500 watts max, and it runs at 24 volts, wild AC, three-phase wild AC. So we're coming down with the conductors 130 feet, and then we're going horizontally in one direction, feeding one battery pack, 24-volt battery pack, 350 feet. Now we're going another direction, 300 feet. Okay, so we have 130 feet plus 350 feet. Let's call that 0.8. Let's call that 500 feet. All right. Who's an electrician? Okay. Volts times amps equals watts. How many amps is this unit running at? About-ish. About 100 amps, 102 or so. All right. 102 amps. If we want if we want 2 to 5% wire loss, 500 feet running at 24 volts, what kind of conductor size do we need? Gargantuan. Huge diameter. So we're going to have a huge conductor about this size running from the tower top all the way down and over to the balance of systems. All right? Can we do it? Absolutely. We're going to do it. We're going to size the conductor to have a minimum of 2 to 5% wire loss, and it's going to cost. And how far can you take that? How big is your checkbook? Okay, here's another installation. Same machine, but wired in a high voltage configuration. So we have 2,500 watt proven on a 126-foot tower, tilt-up tower, 2,500 watts, running at 300 volts, AC, wild AC. So we're coming down 126 feet, and then we're going over about 300 and some feet to the balance of systems. So let's say 500 feet again. Okay. How many amps are going to be running at? About 8 amps. About 8 amps. What's the conductor size? Infinitely smaller. Now we're looking at maybe a number 6 or so coming over from the tower top all the way down and over to the balance of systems. Cost difference? Gargantuan. You're going to have 3 of these, and you're going to have 3 of these also. L1, L2, L3. And so we can go greater distances with smaller conductor sizes with the high voltage machines. Less monkeying around. So again, how far can you go from the machine to the balance of systems? Depends on your pocketbook. How big is your pocketbook? How much you want to spend. And we're going to talk more about that when we go into siting the machines. So now we can go greater distances with these high voltage machines to where potentially where there's a better site at the same cost or less. Here's another crossover machine, the 2,500 watt proven, 400 pound machine. This is just a beast, and a long living machine. The manufacturer of this wind machine builds farm equipment and builds wind machines on the side. So they took their knowledge of farm equipment, big bearings, lots of metal, and used that on the wind side too. Big bearings, lots of metal, slow speed. Used to be an affordable machine in the United States till the dollar tanked, and now it's extremely expensive. They have a 600 watt, 2,500 watt, 6,000 watt, and a 15,000 watt machine. All look the same, just look like they're on steroids. Now we're going into the arena where we're going to have machines that are going to produce some of our electricity, up to machines that are going to produce all of our electrical needs. On the bottom end is the Whisper 500, just discontinued this fall. You can buy them by the bushel on the internet. Bad reputation. It's the only two-bladed machine out there. There's another two-bladed machine out there. One of the only two. You get what I mean. Two-blade machine just would tear itself up. Low bearing life, short-lived, utility intertieable, very, quite easily, but it just doesn't have the endurance. Jacob's Lawn Case still can get these. Nice machines, 3,600 watt output, long-lasting. The endurance. Now we're entering into an area which is radically different from anything we've talked about so far. This technology is based upon wind farm technology. They took the knowledge from that, applied it to this machine, and they really have something now. So this machine was originally rated at 3.6, bumped it up to 4.2, and now is re-rated as a 5 kilowatt machine. And this is what it looks like under the nacelles. Fits within the parameters of a pallet. And now, remember, if you remember back on, I told you that most wind manufacturers in the United States are mom and pop operations. They're going to batch out components, make a batch, and then assemble them, sell them, take orders, do another run. Well, this machine is different. Essentially, I don't know if all the components, but I think almost every single component on this machine has another application. So they're taking stuff off the shelf and making a machine. So you can go to Grainger, you can go to supply houses and get parts. You don't have to wait 6 months to get a part. And I think that's the magic of this machine. So let me give you a little bit of background. So on top of this machine, somewhere is going to be an anemometer, a wind speed indicator, that looks something like this, with 3 cups on it, not 2. And it's going to be sensing the speed of the wind all day, every day, just like a big machine, utility-grade machine. So this machine has a brakes on it, and the brakes are going to be set, the brakes are going to be normally closed, normally on. And it's not until the machine is, the anemometers, the computer system, sees a wind speed of, do you know, what's the cut-in speed? Is it? About 4 meters per second, 8.6 miles per hour. 8.6. So the anemometers need to see, say, a 9-mile-an-hour wind in order to say, and that tells the computers, like, okay, we got something here we can work with. Any wind speed below that, the brakes are on, the rotor's set, nothing's happening. Then there's going to be an upper limit as well. Do you know what the upper limit is? The cutout speed? Yeah. Yeah, it's 54 miles per hour. So at 54 miles per hour, anything greater than that, the machine is going to shut down. So we have a window that this machine is going to operate in. Anything below or above that, the brakes are set. Nothing's going to happen. All right? So we have our machine shut down. Here's the braking system right here. Here's the brake disc. And then there's air brake here, Bendix air brakes. Normally closed. All right? So the machine is shut down. Nothing's happening. Anemometers sense a wind speed of greater than 9 miles an hour for X amount of time. And it tells the computer, or the computer tells the machine, okay, we got something we can make energy with. So a compressor underneath this unit fires up, pumps up the air, opens up the brakes, and the rotor's free to spin. What happens next? Power comes up from the tower, from the bottom of the tower, comes up to this motor right here, spins this AC motor up to 1750 RPM, all right? And when that motor's up to speed, as it speeds up, it's transferring power to a gearbox, down to this drive shaft, to the rotor right here. This is where the rotor bolts in. So our rotor is now up to speed, 200 and some RPM. Now the wind is going to take over. As the wind tries to drive the rotor faster, we're going to the power now is not going to the rotor. The power is going from the rotor to the drive shaft to the gearbox to the motor. Now our motor is a generator. All right. So we're trying to overspeed that motor. We're locked in voltage and we're locked in frequency with the utility. And as we try to overspeed the motor, we're going to get amperage output. All right. And the greater the wind speed, the greater the amperage output. All right? So now we have a machine that's going to put out utility grade AC, 240 volt, down the tower, plug it into a breaker essentially, and that's that. We have a machine that we can get components off the shelf, locally or nearby. And I think this is a cat's pajamas right here. A little expensive just now. But do you know how many are out there? Do you have any out there?
There's roughly probably anywhere from 30 to 40 throughout the United States. Mm-hmm. We just put one up in Hoopeston, Illinois, which is just across the border. It's running like mad, and the energy output that you had on the previous slide mm-hmm. has also gone up since the kilowatts rating has gone up.
Oh yeah.
So you're looking at an average of 10 miles per hour. You're probably going to get 8 to 9,000 kilowatts in a year. Mm-hmm.
Almost as much as you need for an average home.
Yeah.
Now, I think this is the second endurance installed in the United States right here, sitting on the trailer.
What's the cost of that?
I don't know what's the cost right now.
That's pretty close, but that's not installed.
Right, 35,000 clams just for the machine. As more of them get out there, the cost is going to come down. Installed cost is
well, that would be determined on the tower size too, and the concrete pad.
Mm-hmm.
Yeah. There's a lot of determinations on that.
In general, the installed cost that Windside assessors use, and this is Wisconsin numbers, about $45,000 turnkey. So parts, labor, everything. You write the check. And that's just a general ballparking. The more complicated the system, the higher the cost. In general, we're talking general ballparking. Fabulous machine. I suspect that machine is going to, you're going to see more of it. Problems. This is Dave Blecker's machine, second one in the United States. Great performer, screaming performance. They've had trouble with the controllers at the base of the tower.
We actually have a second-generation control box
mm-hmm.
now, and updated our software too, so we've had no problems going forward.
Yep. And these guys, I've talked to these guys out in, what are they, Utah or Idaho or somewhere. Really nice guys. You call them up, you can talk right to the people that make this. Great people. And they come to the Energy Fair. Third week in July, by the way. June. Third weekend in June. Proven, this is a 6,000 watt version of the 2,500 watt machine. Great performer from Scotland. Berge XL 10 kilowatt machine. Tended to underperform. Great performer. And then they had trouble with noise off the rotor. That was an issue. So Berge took and cut about a foot off the blades to quiet it down. They retooled the airfoil on the blades. And this machine should have been rated at about 8,000 watts. They retooled the airfoil, retooled the blades, and now they lengthened the blade out where it should be. Now the collector is a 10 kilowatt collector. 10 kilowatt machine. And so you can take these older machines that had the shorter blades on and put the normal 10 kilowatt blades on them, interchange those very nicely. There's 1,000 of the bushels of these machines out there of all different ages, very reliable machines. ARE 442, This is, again, a 10 kilowatt machine. This is Robert Preuss's machine. Remember, he took the AWP, retweaked it, made the ARE 110, made that a 2,500 watt machine. Well, this is a larger version of that. And word on the street is that they've tweaked it so much that they're getting vibrations and harmonics off this that are really loud. And I didn't know what does loud mean. Well, when you run a coil of wire through a magnetic field, you get these vibrations, these harmonics that are built up in it. And if you put your ear up to the tower, you can hear the humming as the wind goes through. You can hear this humming noise in the tower. Well, 100 feet, 200 feet away, 300 feet away, you can hear the noise of this machine, this humming noise, as it spins up and spins down with the wind speeds, and that's unacceptable. People don't want to hear that, and people's neighbors don't want to hear that either. So Robert Preuss is trying to figure out how to quiet this machine down, and if he can't do that, that's going to break his company. And it's a fabulous machine, high performance machine. People have seen this machine put out as high as 1,600 watts instantaneously, and then comes back down. And look at the production numbers on it, just screaming. Here's a 10 kilowatt Berge, 6,240 kilowatt hours per year, versus same nameplate rating, over double the output. So if they can't lick this problem, they're going to be out of business. And word on the street that they got problems. Now we're into machines that have more sophistication. Everything we saw previous to this is direct drive, except for the endurance. And we have 6 wear points, 2 on the generator, 2 on the yaw mechanism, and 2 bushings on the tail. Now we're getting into a commitment to a piece of equipment. Now we have a relationship that's going to go far beyond just every 6 months we're going to go up and do a visual inspection. Now we're going to pull up buckets of grease and oil, and we're going to pull up grease guns, we're going to pull up tape, all sorts of stuff. Something on the machines that prior to this, you and your friend are going to go up in the tower, and you're going to spend more time climbing and inspecting the tower than you are going to be working on the machine. Now you and 4 of your friends, 3 are you going to go up and spend half a day up on this machine, and then you're going to have a buddy on the ground doing groundwork, running buckets up and down on a pulley and rope. This is the Jacobs 3120, built in Prior Lake, Minnesota. 31 is the rotor diameter, 31 feet. 20 is the output, 20 kilowatts. So now you and your 2 buddies are going to climb up to the top of this machine, take the covers off and the shrouds off, and you're going to replace the grease. Well, do an oil change. So here we have a horizontal rotor transferring power horizontally to a gearbox, and the gearbox is going to transfer the power vertically through a drive shaft to the alternator located down here. It's nested in the tower vertically. So every turn of the rotor, 1 turn of the rotor, equals 6 turns of the alternator. We have more stuff going on here. 96 wear points on this machine. What kind of service work is on that? Lots. So you and your friends are going to climb up to this top of the machine, take the shrouds off, and you're going to hook in, stand on top of the braking mechanism, and at the base of this gearbox, you're going to open up a valve, drain out the oil, 90-weight gear oil or synthetic oil, into a bucket, and you're going to capture that. And you're going to close the valve, lower the bucket down, you're going to bring up fresh oil, and you're going to take a plug out of the top, put a funnel in, and stand on your tippy toes, and you're going to dump the oil into the gearbox. And as you're dumping it into the funnel that's going into the gearbox, the wind is going to catch the oil and run it down your arm, and it's going to drip down yourself, drip down all the metal bits of the machine down through the drive shaft onto the braking mechanism. And then you're going to lower the container down, then you're going to bring up all the grease rags, and you're going to wipe down everything else. Just a filthy job. And then there's going to be You're going to grease the rotor. You're going to inspect the rotor. You're going to grease the governor, all that jazz. You're going to spend about half a day up there if you don't find anything else wrong, assuming nothing else goes wrong. Screaming performance. This is this machine is turnkey install cost $77,000. A ARE 442, which is a 10 kilowatt machine, install cost $71,000. So our next is $6,000. You can get twice the performance. And this machine really performs, but it's going to be breaking down all the time. It's just going to be a headache, and lots and lots of time up on the tower. This is going to be this is a hobby right here. This is our machine at our office. When it runs, it's just a screamer, but you're going to be doing service work on that thing. More on that later.
Hey, did they get software kit for that yet? That one?
Pardon?
Did they build a software kit for that one yet, to where you can monitor it on your computer? I know they were talking about doing that.
I think the new inverter. There's a new inverter that's coming out. I don't know if I think it just got UL listed. I don't know. It's a $20,000 or $11,000.
Yeah.
It's an extremely expensive inverter, but it does a better job. APRS World does our monitoring on that machine.
Right.
That machine.
Right.
And so we go through APRS World, and so we're looking at real-time production versus wind speeds and all that.
Who is that one?
APRS World, and that is James Jefferson Jarvis, J3.
Okay. We got a guy
from Minnesota. Starts with an M.
I'll look it up.
Yeah, real nice systems.
And you weren't kidding about the maintenance.
Yep, just a nightmare, but it does great performance though, at a low cost. Now, this is the Vestas V15. Now we're looking at machines that are old wind farm equipment. So this stuff was out in California, taken down, new machines put in their place, higher outputs, and they're being refitted in South Dakota and coming into the Midwest. So this is for small farms, small commercial applications. 30 kW, 60 kW, and 90 kW machines. Now we're looking at 11,000, 12,000 pounds just for the machine. This is huge. Big man baskets up on top, so you get 6 people up on top. Hood just like a car. You're going to pop the hood open. Then you're going to have a transmission down in there and braking systems and all sorts of stuff. No tail on it. This is an upwind machine. So we're going to have a giant bull gear and servo motors that are going to orient the rotor into the wind. Also, we're going to have a link from this machine through the internet to the shop, the installer shop, which may be 300-500 miles away, and they can go into this machine and look at the parameters, tweak the parameters on a seasonal basis, or troubleshoot this machine from their shop, take what they need and go to the site instead of loading up the truck with everything they think they need and then going to the site. This is going to put out single or three-phase utility-grade AC in usually 240 volt configurations. But it's made for small farm commercial applications. Single phase or three phase. Oh, shit, yeah. Yeah, in 2 minutes, is that okay? Here's the a Berge. 6 wear points, 2 on the generator, 2 on the yaw mechanism, 2 bushings on the tail. This is the schematic for the Jacobs 3120, 96 wear points. Just a god-awful lot of stuff going on in there. Lots of maintenance. Okay, let's take a, this is what I would like to do. I would like to take a 10-minute break and start up at 5 minutes after the hour.
Clay, this is Chad over here. We're sorry.
Yeah, yeah.
We're scheduled to take a lunch break here at noon.
Yep.
And what we would like to do, we have a half-hour scheduled, but because of some of our remote locations being a distance from an eating establishment, we may go to 45 minutes.
Let's do 45. Yep.
Okay. And then for all of us here in Fendler, you can go over to the Union across the street and down the stairs. There's several eating establishments over there, lots of variety that you can do, Starbucks and Asian food, whatnot, and we'll meet back here at 12:45.
12:45. Yep.
Okay.
Yep. 12:45. We'll start up right on the dot. Okay. So think of some questions. We'll start out with a question and answer period, and then we'll keep rolling. Thank you.
There is also a cafeteria in Stone Hall.
Stone Hall is just directly across the street, so if you'd like to head over in that direction, there's an option as well.